Hello, this is Mark French, and this is another in a series of short videos on how to use MathCad. Today I'd like to talk to you a little bit about how to solve differential equations using MathCad and show you how to solve a particular kind of differential equation called an initial value problem. Let me show you the equation we're going to solve. I'll just scroll up here and push this up. There. That's the initial value problem. Y prime, that's the slope of y, or dy dx if you prefer to write it that way, is the square root of the sum of x plus y. Now that describes a family of curves. Now you got to remember, the solution to a differential equation is a function, not a number. The solution to an algebraic equation is a number. The solution to a differential equation is an algebraic equation, or a function. So our goal here, the game we're playing, is that we're supposed to find a function y of x really, that makes this expression true. The slope of y with respect to x equals the square root of x plus y of x. Now that defines a family of curves. In order to know which one exactly we're going to find, we need to know one point along that curve. And that point is what's called the initial value, where x equals 0. We know that y equals 0.2. This is just a function I made up. I don't know that it has any physical significance, but it's a nice problem to work on in a situation like this for a tutorial. Let me show you what the vector field looks like. This is the field. This is defines the family of curves that is described by this function right here. If you look at that point right there, that's the initial value. Now I'm using what's called a vector plot in MathCad to make this plot with all the arrows on it. And it's really a matrix that I'm plotting here. And along the x-axis, that tells me where I am in the matrix. That's column 1, or column 0, column 1, column 2, column 3, and so on. And that's row 0, row 1, row 2, and so on. All right, now I've got this set up so that dx and dy are both 0.2. So that's 0, that's x equals 0, x equal 0.2, x equal 0.4, and so on. That's y equals 0, y equal 0.2, y equal 0.4, and so on. So that point right there is x equals 0, y equal 0.2, and that's because dx and dy, the width and the height of those little boxes, are both 0.2. So that means at x equals 0, y equals 0.2, that's that point. And then as I move away from there, the line I draw simply follows the arrows. The arrows tell you where to go, right up there. If you're into aerodynamics, you might think of those as streamlines. That's essentially what's going on. Now I'm going to show you two different ways to solve this problem. The first one, I'm going to use a function called Odesolve that's in MathCad. Okay. Let's see, let's call this solution method 1. Let's spell it right there. One more try here. There we go. Solution method 1. That's Odesolve. That's a function in MathCad. Now note that when I started typing, the font changed as soon as I hit a space bar. When you first start typing, MathCad assumes you're typing a variable or a command. As soon as you hit a space bar, MathCad knows there's no such thing as a command or a variable that has a space in it, therefore it must be text. So watch this. Text, test, how about text? Right now I've got, I guess that's probably Roman type. If I hit a space, see how it changes? That's how I went from being potentially a command or a variable name to being text. Alright, so in order to use Odesolve, we use a solution block or solve block. And the way you start a solve block is with the command given. Now that's not text, that's actually a command. And you see that the font is different. That's, again, that Times Roman, I think. So we say given. So what next thing we're going to do is we're going to define the equation we're going to solve. So we're going to go y prime of x. Now hit y. To get the prime, you hit Control and F7. Okay, that's not just a text command, that's Control F7. That means something mathematical. Now, we're going to use the control equals, that bold face equals, where I'm telling MathCad something. I'm making an assignment here. And then I'm going to define the right-hand side of the equation, x plus y of x. Okay, so there's the differential equation defined. And the next thing I need to do is define the initial condition. So I'm going to say y of 0, and again, control equal, not just equal, 0.2. All right, so there's the beginning of the solve block with the given command. There's what lives inside the solve block. In order to close the solve block, I have to tell MathCad to calculate something. In this case, I'm going to use a function called Odesolve. Right? Last thing I need to know here, by the way, is I need to know how far I want it to calculate y of x. I need to know the range of x. If I assume that the first value of x is 0, I'm going to say the last one is 2. I just want to go, that means I'm going to solve this differential equation in the range from x equals 0 to x equal 2. So now I can say for Odesolve, I'll say y, and I'll call this maybe y1 for solution method 1, equals Odesolve. And Odesolve, in this instance anyway, is going to have two arguments. The first one is which variable I want it to use, and that's x. That's the independent variable. And I need to give it the end of the range to solve over. And it's going to sit there. You say, okay, it's done calculating. Now I can go ahead and plot the result. All right. Now I just hit, let's see, control graph. If you see right there, I just hit the ampersand sign. That's a shortcut that pulls up a xy plot for me. So say x and y of x. And I want to go from 0 to x final. And because I want this to be square, I'm actually going to go from 0 to x final here. Now I know this is the y-axis, but the plot I showed you before, the vector plot, was square, so I'm going to make this one square too so it matches. And let's see why I didn't like that. Oh, because y1, not just y. There. Okay, and there's the plot. Now let me throw some grid lines on there. And those are pretty much square. Now you can see that looks an awful lot like the vector plot that I showed you above, right there. Okay, those look very similar. Now there's another way I could do this. Now this isn't a function in MathCad. This is just a solution method that's been around for a long time, and it's called a finite difference. Okay. Now let's call this what do I call that? Solution method 1. I'll call this solution method 2. Finite difference. Alright, now you can go look up how to do finite differences, but basically everywhere you see a slope, you put an expression in where you have the difference between 2 points along a curve divided by delta x. You use actually a finite approximation to the infinitesimal slope. And if I do that, I can write the equation down and just step through it in step fashion. So this is going to be calculated at discrete points of x. And let's say right now I want to have 100 points in my solution range. So I needs to go from 0 to n. I is going to be my range variable that keeps track of all this. My initial value of x, I want to be 0. Let me move those over a little bit. And I want my final value of x to be 2. All right, just like I had before. Now I need to know what delta x is as I step through. So to get a capital delta, you can either go up to the, let's see if I find the toolbar here. View, toolbars. There's a Greek toolbar right there. Also, most of the characters on the keyboard, which are Latin letters, have a Greek letter that goes along with it. So if I say capital D, then I hit Control G, I get a capital delta. All right, so there it is. Delta x equals x final minus x initial divided by delta x. Now if I did this right, oops, not delta x, by n. There we go, that looks better. And delta x should be 0.2 for 0.2 if I did this right. 0.2, sorry. So there we go. And I'm going to do one other thing. I'm going to say define my starting point. Now, up to now, the subscripts have been text subscripts. See that dot right there, and right there, and right there, and right there. That I literally just hit a period on the keyboard, and that's a text subscript. That doesn't have any mathematical meaning. It's just text. Now, I'm going to use a mathematical subscript to make a vector of numbers here that I'm eventually going to plot, and that'll be my solution. The vector subscript, so for y, the very first value of y is going to be y sub 0. I use the left bracket command right there. Y sub 0 defined as 0.2. That's my starting point. All right, that 0 right there has mathematical meaning. That is the 0th position, or the very first position in the solution vector. Okay, that's an actual vector address. MathCad always starts at 0 being the first vector address, although you can change it to 1 if you like, or to anything else if you like. So the next thing I need to do here is I need to find a vector of x's, again subscript I now, we know these up front. These are the independent variable, or x is the independent variable. So I can make the vector of x's up front. I don't need to calculate those using the differential equation. I can just define those. So that's what I've done here. In fact, if you want to see, there they are right there. Okay, 02, 04, 06, 08. So you can see I'm stepping by the right amount. Okay, last thing I need to do is I will have written the left side of the differential equation out as a finite difference and then solved for y of I plus 1, the one I don't know. Oops, I plus 1, there we go. And if you do a little algebra, you wind up with this expression. You can, offline, maybe you can convince yourself that I have it right. I think I do. And there you go. So, believe it or not, I'm ready to go. I'm ready to plot. Okay, let's call that y2 maybe, since I have y1 up. Let's just leave it like it is. We'll just leave it as y. All right. So now what I can do is call up another plot. Again, I just hit the ampersand and say x sub I and y sub I, and there it is again. Okay, now it looks a little different because I've got different limits on the axes here. So let's make this the same as we had before. And we'll make that x sub f. And we'll just hardwire the 0 in there. There we go. That should look an awful lot like it did before. In fact, we'll even put the grid lines on there. Again, looks pretty good. Let me change the aspect ratio a little bit to make those boxes a little more square. That looks pretty good. Now, how do I know I have this right? Well, let's try this. If y of I, y sub I is my finite difference approximation, y1 of x sub I is what we calculated using the ODE solve. And there it is. You can see those two things lay right on top of each other. They're hardly distinguishable. There's just a little bit of error, and that's because the finite difference approximation is not exact. If I want to make so the red line and the blue dotted line, in fact, let's make that a blue solid line. If I want to make those closer, all I really have to do is make delta x smaller, make that number right there smaller in my finite difference approximation, and the finite difference will become closer and closer to the actual derivative. So there you have it. We've defined a simple initial value problem, differential equation, and solved it using ODE solve and finite difference approximation.